not ideal.
Okay, it's 7:32, so I guess we'll start now and we can talk about the weather after, or you can chat amongst yourselves.
Chat amongst yourselves.
Okay. All right, so welcome to the December regular meeting of the Edmonton Centre, the Royal Astronomical Society of Canada. In case anyone doesn't know, I'm Jeff Robertson, the president, for one more month. It's our last meeting of 2020, a year most people would be glad to see the back end of, and it's been a trying one for all of us. Many of the things we'd like to do in 2021 will still not happen, but there is hope that later in the year a sense of normality will return. And I see they started with the virus, but it's going to be many, many months before it works its way down to us. I'm glad I didn't see him sign in, but I know most of us saw that Denny had a bit of a health scare, and I'm glad he's okay and he's on the mend. Okay, we'll start with the minutes. So Mike, if you'd like to do that.
Yes, so the last meeting was November 9th, and the minutes for the meeting have been posted on the OneDrive. Is there anybody to report any errors or omissions at this time? Okay, then I shall move to accept the minutes as posted.
Okay, can we have a seconder? Just speak up. Anyone?
Martin's
Franklin?
seconded.
Oh, who? Okay, Franklin's waving. All right, let's make Franklin second that one. All right, anyone opposed? Hearing none, we'll say they're carried. Okay, our featured speaker tonight is Dr. Tyrone Woods. He is a Plaskett Fellow of the NRC Hertzberg in Victoria, BC, and he studies the physics of some of the most energetic events and objects in the universe by combining theoretical models with observations across the electromagnetic spectrum. Before returning to Canada, he completed his PhD at the Max Planck Institute of Astrophysics in Munich and held research fellowships in Australia and the UK. He tells me that he does have family in town, so perhaps when this thing ends, he can visit us in person at one of our meetings. He's with us tonight via Zoom to speak on the subject, Titans of the Early Universe, the birth of the first black holes. I give you Dr. Tyrone Woods. You've got the floor.
Thank you very much. I'll give a shot at sharing my screen here. And the immortal 2020 questions. Can everybody see my screen? Can everybody hear me?
Yes, on both counts.
Yes, yes.
So, thank you very much for having me. Yes, no, my wife and I are both from Edmonton, and we still got a lot of family there, and it's great to speak to a hometown crowd, even if it has to be virtually this year. But I think that by this time next year, at least, should be a good chance we'll be able to come and visit in person. So I'm looking forward to that. I'm also very happy to speak about probably my favorite subject these days, which is all of just the cavalcade of amazing scientific discoveries that are coming out about black hole physics and black hole astronomy. And really, in the last few years, it's been incredible. I mean, we've had the gravitational wave astronomy has gone from a dream to a fully fledged field of astronomy. Really the next big thing, and we've been seeing black hole mergers from across cosmic distances. We also got the first image of a black hole, actually a supermassive black hole, the first direct image, the black hole in M87 just last year. And really, there have been news stories coming out every few months about this or that big discovery in black hole physics. Most notably, not one but two Nobel Prizes in physics awarded for black hole astronomy and black hole physics in 2017 for gravitational waves, and for a couple of things that I'll get to in 2020. So it's not hard sell for me. I'm a big fan of black holes, in case you couldn't tell. But if I didn't know better, I would think that something must be going on here, because this is an awful lot in just a couple of years about black hole physics. I think part of it is probably that that black hole physics and black holes generally very much captured sort of the popular imagination. And we see this in movies and in TV and even in music. Sometimes, faithful representations or attempts to be as scientifically accurate as possible, like in the film Interstellar a few years ago. Sometimes not so much, like a recent, well, not too recent, a few years ago, Halloween episode of The Simpsons. You might say, oh, it's just a cartoon, but I for one know that a lot of the writers on the Simpsons staff are actually former mathematicians and physicists, so they really should have known better. But it was a funny episode. But more than just capturing the public imagination, I think that one of the reasons we're hearing so much about black holes lately is really well encapsulated in a quote from Robert Dycraft, who is a senior scientist at the Institute for Advanced Studies in Princeton. He was commenting on the first image of a black hole by the Event Horizon Telescope team last year, when he said the black hole is the atom of the 21st century. And what he meant by that really was he was speaking in reference to in the 20th century, at the beginning, whether you were trying to understand what was powering the stars, what was their fuel source, or the interaction of light with matter, or just fundamentally how particles interact with each other. There was no getting around. You needed to understand the atom. All roads led to the atom. And for better or for worse, trying to understand the atom just dominated every question really about physics in the 20th century. General relativity. We don't know how these work together. We don't know how these branches of physics meet exactly, but we know where they meet, and it's in a black hole. And I think this is really the key reason there's been, along with a lot of technical developments along the way, one of the key reasons that black holes are getting so much attention now, particularly now that in the 21st century we have the tools to really try and understand these in depth. So, by the way, I heard a microphone there. Please jump in at any time if you have any questions. So what do we mean, though, when we're talking about a black hole? There's a lot of popular conceptions, but physically, what are we trying to get at? So the idea actually goes back quite a ways. The first written record that we have of any notion like a black hole was put down by John Mitchell, a philosopher and a really a polymath, a multi-talented scientist, 230 some years ago, who was thinking, and I think this is remarkable considering it was 18th century England, about the statistics of binary stars, dual stars, solar systems with two suns. And in doing so, he first conceived of the notion of an object with such powerful gravity that maybe light could not even escape. And he didn't have the mathematical tools to really pursue this idea any further. But he did have one really critical insight, which was that even if we couldn't see these objects directly, we could infer their nature and come to understand their properties from the way that these dark stars, as he called them, interacted with companion stars or surrounding gas with their environment. And this is really at the heart of how we try to study black holes astronomically today. Still holds up. Now, as I said, he didn't have the mathematical tools to really pursue this further. That had to wait for the 20th century and ultimately for Einstein to really set off on his miraculous run of discoveries. In particular, devising special relativity and showing us that there's no such thing as a distinct space and time. They're inseparably linked, hopelessly muddled together in this thing called space-time. And also that, of course, mass and energy are really two sides of the same coin. He also then showed in 1915 his general theory of relativity, where he folded gravity into these ideas and showed us that mass, anything with mass, curves the fabric of space-time, and the curvature of space-time in turn guides the movement of masses. Gravity, as we experience it, is really just a manifestation of the curvature of space-time. And there are many, many beautiful representations of this. This is one that I rather like because it shows both the Earth bound in the curvature of space-time wrought by the sun, but it also shows us how this space-time curvature could conceivably bend, well, it does bend light. In fact, this was one, as light tries to follow just the shortest possible path, inevitably it follows this curvature. And this was actually one of the earliest demonstrations that there really is something to this general relativity, waiting for a solar eclipse and trying to observe light from background stars bent in their trajectory by the curvature of space-time wrought by the sun. So another proof came from the ability, using approximate solutions to Einstein's equations, to accurately model subtle effects in the orbit of Mercury, very famously. But a general exact solution for how a point mass, a massive object would curve space-time came not from Einstein but from Karl Schwarzschild, actually shortly before he died. And from him, we got the first notion of what is now known as the Schwarzschild radius. I spent some time learning. I'll try to pronounce his name properly. And this is really the first formal notion that, with a rigorous backing, that if for a given mass, there's a characteristic size where if we compress that mass down to that size, not even light is going to be able to escape from the surface. Of course, at the time, this was mostly thought of as a mathematical curiosity, or maybe a useful, interesting way to try and constrain the masses of stars. Eddington was argued that they're the most bloated and distended stars that had been observed could not possibly be as dense as the sun because they would collapse. They would be black holes. But the idea that this was something that was real and physical and not just fun with math really only started getting going in the 1930s. And really the first step came from my favorite historical physicist, Subramanian Chandrasekhar, who, while he was traveling from India to the UK to start his PhD, which he had to do by boat at the time, of course, found the time to, just casually start off his career. Actually, he published a couple of papers, but start off more or less his career by showing that there must be a maximum mass that a white dwarf, we now know the spent leftovers of stars, like our sun, could reach before they would collapse in on themselves. Now, this idea was also greeted with skepticism at the time. Most people generally thought, well, sure, it's interesting, but it's so weird that there's just got to be a law against it. There must be some physical principle that prevents these stars from just collapsing and collapsing. And anyone for being confused at this time, because we were really just beginning to understand really how stars evolve, how they live, how they die, what fuels their long lifetimes. And we now know, of course, that at their heart, stars are fueled by nuclear burning, as hydrogen burns to helium, burns to carbon and oxygen, which is where stars like our sun get off the train, blowing off their outer layers and leaving behind white dwarfs. But more massive stars continue burning to neon, to magnesium, finally silicon, and then to iron. and of course, and the merger of, the fusion of iron nuclei does not lead to a net release of energy. It actually soaks in energy. And so instead of nuclear fusion releasing energy and holding up the star, you have a runaway collapse. Now, it was about a year after Chandrasekhar wrote his paper that we discovered the neutron. And Robert Oppenheimer and others, who would soon get distracted working on the nuclear bomb, showed that Fermi pressure of neutrons, the desire of neutrons not to be on top of each other, could provide an additional force which could hold up further hold up a neutron star against collapse beyond the Chandrasekhar one with the white dwarfs, but in an analogous manner. But this would be a remarkable object. You're talking about something, with the density of an atom, but on a scale, it would be the width of Edmonton, but the mass of a little under 1.5 times the mass of our sun. Just a teaspoon of it would weigh 10 million tons. So people, again, generally thought, okay, this is interesting, more and more theory, cool, but I'll believe it when I see it. Of course, finally, in the 1960s, we did see them with the observation of radio pulsars from some of the from Jocelyn Bell working in the UK. These were soon understood to be rotating neutron stars with pulsed emission from near their poles, sweeping over the Earth, and this inspired a whole field, a huge area of astronomical endeavor unto itself, including many people working today. It also inspired a pretty cool cover for a Joy Division album. But relevant to the story here, it was an essential part of a revolution that was happening in general relativity in the middle of the 20th century, really trying to get to the bottom of how general relativity works, and all these crazy things we're predicting. Are these really there? Are we making a mistake? What's going on? And a lot of really essential foundational work came out around this time. So Roger Penrose and Stephen Hawking showed that black hole singularities, as they were these points where things go to infinity, are a real prediction. This isn't just a mistake in the math, that if you change the way you would set up the problem, you'd be able to sort of make these go away. These are really a prediction of general relativity. And around the same time, Kip Thorne and Rainer Weiss were just starting to tackle the problem of how you might actually be able to go about measuring gravitational waves, which would ultimately culminate in the LIGO discoveries. These four would have all gotten Nobel Prizes. Unfortunately, Stephen Hawking passed before he had the opportunity, but the three others, of course, have now since gotten their Nobels. And we also saw a lot of work from Werner Israel at the University of Alberta, as well as others, towards the emerging notion that for all of the complications of black holes, ultimately, they can be described by just three parameters, just three quantities: how massive they are, how quickly they're spinning, and whether or not they have any electric charge. At least within the context of general relativity, that seems to be all you really need. The saying goes that black holes have no hair. There's no extraneous things you need to know about them in principle. Now, as this is happening and following on in the ensuing years, we started to actually find real-world counterparts, plausible and eventually confirmed counterparts to these originally totally hypothetical, crazy black holes. A number of individual black holes with masses several times that of the sun were found accreting matter from companion stars in tight orbits. One of the first we found in X-rays was SIG-X1, discovered from a rocket probe in 1964. But actually, the nature of SIG-X1 was debated for many, many years thereafter. There was a long-standing bet, actually, between Stephen Hawking and Kip Thorne over whether it would actually pan out to be a black hole or not. Stephen Hawking was the pessimistic one, and he ended up having to pay out, I think it was $1 in 1990. But before that, there were actually a number of other candidates that actually were pretty convincingly confirmed. One of them, LMC X3, was studied by a group from the Dominion Astrophysical Observatory here in Victoria, where I'm based now, using a telescope in Chile because it was an object in the LMC. But they were able to show, using basically the same line of reasoning as John Mitchell was following, was thinking out 200 years earlier, that there had to be an unseen companion to the star that was observed in this system. It had to be about 8 or so times the mass of the sun, and it had to be a black hole. There was just no other way to explain it. Today, trying to understand how these stellar mass black holes, as they're called, work is still a very active area of ongoing research. There's lots and lots more to learn still. Lots of theoretical studies and observations from the radio all the way up to X-rays. And a lot of work is being done on this front by folks at the U of A. Now, of course, probably the most famous demonstration that black holes are really out there, these stellar mass black holes, was the gravitational wave discovery announcement back in 2016. That we had finally, after Einstein himself had dismissed it as, gravitational waves were far, far too subtle an effect to ever actually detect, we found a way to do it using the most precise measurements that have ever been made using these devices called interferometers. We were able to measure, to an accuracy of the width of an atom, subtle fluctuations in space-time from the perturbations originating in a merging pair of black holes out at cosmological distances. And now this is, after just a couple of years, it's almost old hat. We're finding, discoveries like this all of the time in newer and weirder types of merging systems. And you've probably heard a lot about the LIGO over the years, but one thing I like to mention, because maybe you haven't heard about it, is that there's actually a very strong Alberta connection. The lead operator for the Hanford site, one of the two sites where they perform these measurements, is Corey Gray, who's actually from the Siksika Nation, just outside of Calgary. And if you haven't heard about him, I urge you to look him up. He has a lot of really great, really cute stories. There's an awesome one about getting his mom to help him translate the first LIGO discovery paper into Blackfoot. It's really great. Now, we're pretty confident about stellar blast black holes. They're really there. It was a long time coming. Another thing that's been, another example of black holes that has been investigated in parallel throughout all this, and actually started out even earlier, began with the so-called quasars, or quasi-stellar radio sources. These were first discovered as radio astronomy started to really pick up steam in the 1950s. And within just a few years, there had been hundreds of these things found, these very luminous point sources in the radio. Now, following up on these things in optical light, and also we also see eventually huge plume jets in the radio as well. Following up on these objects in optical light, we discovered that they had emission lines, very strong emission lines, which were clearly redshifted due to the expansion of the universe. These things must be at cosmological distances, very, very far away, which meant they must be extraordinarily bright. And we also found that their brightness varied on short time scales within a year. Now, if you're professional, now if you're an astronomer, you might immediately think, as soon as you hear a time scale, I know the maximum size, the physical size that this thing could actually be. And the reason is, if you're seeing something varying, some information is communicating from the center of the source out to the periphery. That variation can't travel any faster than the speed of light. And so if we have a time scale times the speed of light, we have a physical size. And the physical sizes of these things had to be very compact relative to the galaxies that we found them residing within. Now, through the 70s and 80s, there were more and more follow-up observations on these objects, and we found analogs in the local universe, active galactic nuclei, which quickly it became apparent were all consistent with supermassive black holes that were on the order of millions to billions of times the mass of our sun, accreting gas infalling within the centers of these large galaxies. But you might ask, what about galaxies that don't have a lot of gas in their centers? Do these have supermassive black holes as well? Galaxies, say, like our Milky Way. Well, this was investigated a very dramatic effect, particularly in the 90s, using large ground-based telescopes equipped with a technology called adaptive optics, a way to correct for the perturbations and variations in the sky, the astronomical seeing, the blurring caused by the atmosphere, allowing us to make very, very precise measurements of positions. And in particular, it allowed Andrea Ghez and Reinhard Genzel and others to carefully track the motions of the stars in the center of our own galaxy. And what they found was that these motions were consistent with orbits around a single compact object. It had to be very massive, roughly 4 million times the mass of our sun, and completely dark. This was proof that our own galaxy hosted a supermassive black hole. And this netted them a Nobel Prize as well. Now, more recently, we heard an awful lot, and I mentioned it earlier, about the incredible success of the Event Horizon Telescope. It's really a network, a growing network of telescopes spanning the globe, which work in tandem to function sort of as a single incredibly high resolution radio telescope. And doing so, they were able to produce the first image of the silhouette of a black hole. This amazing high resolution image that you see in the upper right of the gas surrounding the black hole at the center of the galaxy M87, which weighs in at roughly 6.5 billion solar masses, which is just astounding. This is very, millions of light years away. We're able to measure not just measure the mass of this black hole, but actually resolve the inner region around the event horizon, which is just amazing. So we know that supermassive black holes exist. In fact, we know that they're actually rather common. There seems to be, we even say ubiquitous in the universe, there seems to be a supermassive black hole at the heart of every massive galaxy, near as we can tell. And throughout, we find these black holes are on the order of millions to billions of times the mass of our sun. But that begs the question, who ordered that? We know how to make a stellar mass black hole, something that's a few times the mass of the sun up to tens of times the mass of the sun. Generally speaking, there are a few islands of mass where things get a little wonky, but broadly, any star that's more massive than about 20 times the mass of the sun is going to leave behind a core which is going to collapse to a black hole rather than form a neutron star if it was less massive. But there's no way, at least in the local universe, that we could make anything that's going to collapse to even thousands of times the mass of the sun, never mind millions to billions. So where could these objects have possibly come from? We know they're there, so how did they form? So the short answer is that we really don't know yet. But we have a lot of clues, and really exciting thing is that a lot of the work in sussing this out is actually happening in Canada with significant Canadian involvement. So one really vital clue is that the masses of these supermassive black holes that we're finding in galaxies seem to be closely linked to the properties of the galaxies that they live in. In particular, Laura Ferraresi at NRC Hertzsprung here in Victoria, and as well as others, have shown that there's a very strong correlation between the masses of supermassive black holes and the masses of the galaxies in which they're found. This isn't just a coincidence. This has to indicate in some way, however supermassive black holes form, their growth must be closely tied to the growth of the surrounding galaxy. They have to be linked together in some way. So that's our first clue. Another clue is that however supermassive black holes are made, they must be able to get really big, really massive, really quickly. We can put a number to that thanks to the fact that light only travels at a finite speed, takes a certain time to travel. The farther away we look, more and more distant quasars, the earlier and earlier in the universe we're looking at quasars and how they live. Surveys, big projects like the Canada-France-Hawaii telescope's effort to map high redshift quasars in the early universe, have found supermassive black holes, rapidly accreting ones, lots of infalling gas, very bright and luminous, that have already grown to 1 billion times the mass of the sun. We can infer this from a number of properties in terms of their luminosity and the emission lines that we see. And they get to 1 billion times the mass of the sun at a time when the universe must have been significantly less even than 1 billion years old, which is astounding. It's actually very hard to come up with a way to accrete that much matter, pile that much matter onto a black hole that quickly. That, combined with our knowledge that that black holes and their supermassive black holes, I should say, and their surrounding galaxies need to co-evolve, need to grow together, has led to a number of theories, but a tractable one, a limited set of ideas that we think might actually work in order to build a supermassive black hole up from scratch. And there are a few different ways you can represent all of these different ideas. This is a very cool plot from Mar Mescla, who was working at the University of Montreal at the time. She's now moved back to Spain, showing different masses of black holes. Let me know if you can't see my cursor. Different masses of black holes and different redshifts, which is just a proxy for the age of the universe. So out at redshift 12 here, that's sort of 400 million years-ish after the Big Bang. And what she's plotted are for different possible seeds, different possible origin mechanisms for how you might be able to make a supermassive black hole, how they would grow up to supermassive black holes. And critically, and I'll get into each of these different possible channels in a moment, but critically, what I want you to take home from this slide, however you might make a supermassive black hole, nature is not going to offer a 100% efficient mechanism for doing so. There are going to be black holes that get left behind, that aren't born in an environment where there's enough gas that they can, or enough other nearby black holes to merge with, that they can grow up all the way to be supermassive black holes. Certainly not by within the first billion years of the universe, and quite possibly not ever. And that means there's going to be leftover black holes, things that are intermediate between the stellar mass black holes that we understand relatively well and now observe regularly in the nearby universe, and the supermassive black holes that we understand well but don't quite understand where they come from. These intermediate mass black holes are notoriously hard to find, but with next generation instruments, we think we're going to be able to find them here and in the distant universe. So I'll say a little bit more about that, but first I wanted to sort of get into the nitty gritty, at least roughly speaking, in terms of what we really mean by all these different models for how you might be able to make a supermassive black hole. So one idea is the light seeds, as they're called, and these are sort of what you see here as POP3 or first stars, stellar seeds, as well as some of these second generation stars. The idea here is basically to make a supermassive black hole. You start with a normal black hole, something that was produced in the death of a normal star, or maybe a first generation star, but nothing too extreme. And then you grow it very rapidly through accretions and mergers with other black holes. And this is sort of the traditionally understood route for how you might be able to build up a supermassive black hole. And there are lots of sort of analogs in the local universe, things that look like what we think this would look like. So generally speaking, the physics here is reasonably well understood. Of course, the flip side of that is that the physics is well enough understood that we think it's going to be really, really hard, we can say with a fair bit of confidence, to follow this route and actually produce something that could conceivably reach 1 billion solar masses within the first, say, 1 billion years of the universe. That comes down to a couple of things. Mainly, there's a limit. There's only a certain maximum rate, called the Eddington limit, at which a black hole can grow before it becomes luminous enough that it starts blowing away any more matter you'd want to accrete. It becomes a self-limiting process, and you kind of get driven back down below the limit. There are ways we think you could get around this, but the trouble there is that even if you could, generally speaking, these black holes, are going to be very, very luminous, very energetic sources. There's going to be jets. Lots of things are going to be conspiring to drive away mass, and it's just very hard to believably force feed these black holes fast enough to grow them to 1 billion solar masses in 1 billion years. So the other idea that is, I would say, increasingly gaining traction, and is something we're working on quite a bit here at Hertzberg in Victoria, is to try to see if nature maybe takes a few shortcuts in the early universe, taking advantage of a few of the special conditions that are there in the primordial universe that really don't exist today. The idea really is that supermassive black holes may originate from initially heavy seeds, black holes that are born already roughly 100,000 times the mass of the sun. There are a couple different ideas for how this might conceivably work. One idea is that you might form a very massive object initially from the rapid coalescence and collapse of a dense cluster of stars. Alternatively, another idea is that rapid infall of gas onto a single object might be able to produce a sort of bloated, extended, but supermassive star-like structure. Many of the, generally speaking, yeah, I would call it a star. There's nuclear burning. It's modestly long-lived. In either case, producing a massive object which then collapses in an environment where it's already being rapidly force-fed gas. The pro here, the advantage of these ideas, is that the conditions under which they form, in which they might conceivably form, I should say, are likely there in the early universe. in particular, we think you should be able to get these very, very rapid accretion rates, these infall rates of gas, because there aren't a lot of ways for gas to cool in the early universe. And if you don't have, in particular, a lack of metals, and if you have a lack of metals and you destroy all the molecular hydrogen, you can produce these atomic cooling halos that can give you, in theory, infall rates at which you pile mass onto the black hole of order the mass of the sun every year, which is the ballpark you need. I would say the biggest con is that all of the biggest problem with these models is that they're still theoretical. They've never before been seen, but on the other hand, we don't expect to see these in the nearby universe because you need certain special conditions like no heavy elements that you only really see in the very early universe, and that we wouldn't have been able to see yet with the instruments that are available today. So how can we tell these two different competing models apart? Well, I would say there are three main routes. One is to try and find intermediate mass black holes, things that have a mass in between the stellar mass black holes we understand and the supermassive black holes we're trying to understand the origin of. We can also carefully examine how supermassive black holes have grown over cosmic time and try and look for trends and make a statistical argument. Or we can try and brute force find black hole seeds, these early forming black holes, directly in the early universe using next generation facilities and try and understand the environments in which they form. And this is something that's going to be possible very, very soon with the imminent launch of the James Webb Space Telescope, which is finally for real. We've already actually, all the proposals are in and everything is set to go after many, many delays. We'll finally launch at the end of October in 2021. This is a next generation successor to the Hubble telescope. It's bigger and it's very sensitive in the infrared. We're going to be able to peer deep into the early universe and find these heavy seeds, if they exist, these black holes that are born already 100,000 times the mass of the sun, shortly after they've formed. We might even be able to find some of the precursor things that produce these black holes. A little further down the line, we're also going to be, a host of new facilities are going to be able to powerfully measure black hole masses out to very great distances, supermassive black hole masses, and provide powerful constraint on how black holes grow overall over time. And one of the very, very important instruments for this is going to be, I think, CASTR, or the Cosmological Advanced Survey Telescope, for optical and mainly for ultraviolet research, which is a proposed successor to the Hubble that would look in the ultraviolet instead of the infrared like James Webb does. And one of the coolest things about this telescope is that it's Canadian-led. This is a proposed Canadian mission that has recently been given top priority in space by the Canadian astronomical community. And you can look forward to hearing a lot more about that in the next decade. Ultimately, perhaps the most definitive answer is going to come from the next generation of gravitational wave detectors, in particular the Laser Interferometer Space Antenna, or LISA, which is a planned gravitational wave detector that will be based in space, not on the ground. This is essential in order to follow the mergers and buildup of supermassive black holes, because they're going to be emitting gravitational waves at a frequency that on Earth is completely swamped out by vibrations in the Earth's crust. There's just no way we can actually do these kinds of measurements on Earth. But in space, it's entirely possible. And this is now planned for launch in 2034, which I think is very, very exciting. So I think in the next few years, and certainly within the next 10 or 15, we're going to finally hone in on an answer as to how supermassive black holes actually come about. But I think the most exciting thing, even beyond that, is everything that we don't understand, that we can't even anticipate yet, that we're going to find out from these next generation instruments. Seeds. You've just got to go for the infrared. But if you want to track the growth of black holes in the sort of the more recent half of the universe, the UV is the way to go, because this is where they're not too redshifted out to redshift. Castor is going to be good out to 2.5 for measuring black hole masses in particular. And these accreting black holes are particularly luminous in the UV. So unless they're, until you get to the point where they're really redshifted, UV is great in the nearby universe.
Chat.
Okay, thank you.
Everything. James Webb far away, UV close.
And it just disappeared on me here.
Jeff, you're unmuted.
What? Oh. Okay, I was trying to read your chat, but it's gone.
All right, I'll state it. On the LISA project that you showed a slide of there, any idea what the scale of those pods are and the distance from each other?
So yeah, the pods themselves are relatively modest, but the distances, they're still, as I recall, trying to decide exactly what the final design is going to be, but it's in the neighborhood of like millions of kilometers.
That's a big scope. Thanks.
Are there any other questions?
I'll ask one. So about the 100, so Tyrone, there's the LIGO discovery of the 150 solar mass black hole, which is, they're calling an intermediate mass black hole, but it's not really the sort that you're talking about probably, right?
No, that was, that elicited some discussion when they called it an intermediate mass black hole.
Do you want to explain that?
Yeah, so okay, there's a couple things to unpack here. So as I said, LIGO has been discovering lots and lots of merging stellar mass black holes. I also mentioned that, give or take a few gaps, things above 20 solar masses, stars that are born initially above 20 times the mass of the sun, generally collapse to black holes. There are exceptions to this. There is a gap which roughly corresponds to not the whole star mass, but stellar cores that are in the neighborhood of 60 to 130 or so times the mass of the sun, where we expect them to blow themselves apart. And so we don't expect, naively, we don't expect to find black holes in that mass range. It's called the pair instability gap. So one of the neat things that happened recently was that LIGO detected a merger of black holes in the pair instability gap. And so the idea was that this must signal there's something going on besides sort of typical stellar evolution, true for definitely either is one way or another, either something very funny is going on, or this is something that has already undergone successive mergers in order to grow as big as it has. There's already been previous black hole mergers. And this led to the idea that, I assume, of calling it an intermediate mass black hole, because it's sort of in this in-between range. And yes, if you wanted to build up a supermassive black hole, this would sort of be the very first baby steps if this was in some dense cluster. But it's not at a redshift where we expect this to be happening. So it's a baby step on the way to being an intermediate mass black hole, but it's not really in that mass range, and it's not really coming about through the formation channel really that we expect. So it's a bit confusing nomenclature.
Thanks.
Thanks, Sean.
All right, are there any other questions?
I've got a question, and maybe it's a dumb question.
No, there are no dumb questions.
Are these things perfectly spherical, or are they Yeah, are they perfect? Even though because they're singularities, are they perfect?
Are the black holes perfectly spherical, or because there's
Yeah,
really
in
what we
terms of their
observe is this
dimensions, are they?
disk that's around it. So I am not a general relativist, full disclosure, but generally speaking, it depends exactly on what you're calling the black hole, right? So if you have a spinning black hole, exactly what you're calling the boundary of the black hole becomes a bit wonky, because you have this, you have a surrounding ergosphere and then an inner genuine event horizon, and you can get, as I understand, and maybe Sherry can correct me if I'm misspeaking. You could conceivably get some deviation here from spherical. But
Okay.
generally speaking, I think it's fair to think of it as a spherical whole.
Okay. Any other questions?
Actually, I'll piggyback on Tom's there.
Go ahead, Russ.
So, given the relative sphericalness, if that's a word, of a black hole, why is it essentially a 2D disk around it? How thick is that disk? Why wouldn't it wrap around the entire mass in some form or fashion?
So there's a couple of things here. So you have in principle, the matter coming in, it doesn't fall straight in. The earliest models for how accretion would work actually imagined, just spherical accretion, just all of the matter comes in from every which direction. The black hole is a sphere, the matter accreting in is a sphere. The thing is that matter has momentum, and will have incoming angular momentum in particular. And so what happens as the matter falls in for a realistic object like this is you actually get a flattened disk of material as matter sort of collapses in along one plane and sort of falls down down the hole. You need a disk basically to get rid of this momentum that the matter has. There's a viscosity to the disk which sends angular momentum out, sends the mass in, and so this is why you have this sort of disky distribution that you always see around these objects. Does that answer your question?
Reasonably close. I guess that would almost indicate some kind of mass imbalance, slightly within the object itself.
Yeah. Well, so there's definitely an asymmetry here, right? And then you get all of these interesting effects. If you look at my illustration of a accreting black hole here, you see there's this faint emission coming out off the top and like off the bottom as well. So you can get very cool things like jets launched along the polar axis that are the mechanism for which is still an area of open investigation. Yeah, there's lots of cool stuff going on.
Jeff, it's Kent. Can I ask a question?
Sure.
All right. We talk about the spin of the black hole. Are we referring to the spin of the accreting matter, or are we referring to the spin of the singularity?
Oh, the black hole itself. So I'm talking about the spin of the. That's a great question. They're all great questions. I'm talking about the spin of the black hole itself, but that is connected to how the black hole is born, and also to the momentum of the matter that is accreting as it falls into the disk. It's going to carry some angular momentum, and in principle, this can add to the spin of the black hole. But when I talk about just three parameters defining black holes, the spin that I'm talking about is just the black hole itself. But they are related.
Okay. All right. Well, thanks very much. That was really interesting.
Oh yeah, thanks for having me.
Oh yeah, and like if you're ever in town, look us up when this pandemic thing is all over.
Absolutely, it'd be a pleasure. Thank you.
Okay, okay, great. If I could get you to unshare your screen. There we go. Okay. Abdur, you're up next.
Awesome, thank you very much. Just going to share my screen here now. Okay. All right, there we go. Okay, awesome. There we go. Okay, can everyone see my screen?
Yep.
Okay, awesome. Okay, perfect. So, welcome to Astroimaging Corner number 105. Oh, that is a wrong one. 1 second here.
It's in my announcements. So.
Yeah, just gonna check other. Selected the wrong option here. Just have to go to the other folder. 1 second. Sorry about that.
That was a tease, Abdur.
Yeah, that is, there we go, Astroimaging Corner. Okay, sorry about that, just having some technical difficulties here, just need to, there we go, Astroimaging Corner. Okay, let's try that again.
It's not shared yet.
Yeah, it will be a soon. Oh, what is going on here? Oh, there we go. Share screen. Okay. This is the correct one now. Okay, awesome. Much better. Sorry about that. Okay, so welcome to Astroimaging Corner number 105. Just going to make that full screen. I can figure out how. Oh, there we go. Okay, can everyone see the screen?
Yep.
Okay, awesome. So our first image for today is from Alistair. Alistair was out at Blackfoot taking some shots of the Geminids. And this one was taken to the Canon 60DA with a 6mm fisheye lens at f3.5. And this was actually a 20-second single exposure at ISO 12800, and this was December 12 to 13 night when Alistair was out there. And this is a single unprocessed JPEG straight out of the camera, and you can see a Geminid going straight underneath the handle of the Big Dipper there. Our next image here is also from Alistair. This is the conjunction of Jupiter and Saturn from December 6. So as you know, the planets are getting closer together, and they will be about 1/10 of a degree apart on December 21st, 2020. And that's just 1/5 the diameter of the full moon. And this is the closest conjunction since 1623 and the closest observable one since 1226, almost 800 years ago. So that will be an interesting event to look forward to. The next shot is from Alan Hawks. This is the Horsehead and the Flame Nebula. And Alan shot this Horsehead and Flame combination from his Edmonton driveway on a night with a 76% illuminated moon. And the combination of high-speed RASC 8 at f2 and proper filtering using an off-long L-enhanced filter and a high camera resolution of the ZWO ASI 2600 HC camera provided the attached photo. And the astrophoto is made up of 77 one-minute guided subs, and this was processed in PixInsight and Photoshop. Great job, Alan. And this next shot is also from Alan. This is titled Midnight in the Rockies, and this is a shot from August 5, 2020. And this shot was taken at Waterfowl Lakes in Banff National Park. And Alan tells us that at midnight, the moon came over the mountains and illuminated the valley and turned night into day. And shot this with his Canon 60 full-frame camera, and this was a 20-second exposure on track at ISO 3200, and the lens I was using was the Rokinon 14mm f2.8 lens. Another great shot of him. This next shot is Bruce's entry for Astro Image of the Year. Well, you have my vote, Bruce. That's Venus under a streetlight during a snowstorm. Not a capture you see every day, not exactly prime time weather for astro imaging, but you got it. Our next shot here is from Murray Paulson, and this is Mars. This is Murray's time lapse of Mars, showing the change in its size from around 21 arc seconds to 13 arc seconds. This year was the closest approach of Mars for the next decade and a half or so, and 2022 will still be pretty good. Mars should be, I think, around 60 degrees above the horizon in altitude 2 years from now. So even though it won't be quite as big, it will be a lot higher up. And Murray took these shots with his Tagashi Lulin 250 NF24 using an ASI 290 color camera. And these were stacked in AutoStacker and processed in Registack 6. The next shot is of Pythagoras crater from Murray. Pythagoras is a pretty large crater measuring about 130 kilometers across, located on the northeastern limb of the moon, and it's named after the Greek philosopher Pythagoras. Our next shot is Mare Nectaris, which I assume means the Sea of Nectar. It's a small lunar sea on the near side of the moon. You can see the striations on the smooth floor of the sea there. And the next shot is the lunar South Pole. And this is Murray's image of the South Pole showing the mountains and valleys on the edge. You can see quite a bit of relief along that edge over there. And the next image is one of my recent ones from a few nights ago. This is the Triangulum Galaxy. I was using the ASI 1600 mm Pro camera with the ZWO LRGB HA filters. This was actually my first actual night of imaging with Hyperstar. So I was using a C11 Hyperstar at f2, and this was a total of 2.6 hours of light gathering. I shot for about 83 minutes through the luminance filter and 25 minutes each from the RGB filters or RGB HA filters. So actually total time was closer to about 3 hours. And I was using the EQ6R Pro mount. And here's a close-up of the same image. You can see a lot of hydrogen alpha regions. Most of those, I'm sure, are many, many times larger than the Orion Nebula, probably similar to the Tarantula Nebula. So there are probably hundreds visible in this image. And the other image that I got recently was the Auriga region, showing Comet Atlas in there. And my main target was actually the 3 open clusters in Auriga, which I've been looking at through binoculars. The cluster exactly in the middle of the screen is M36, which is the pinwheel cluster. The one at the bottom left of the screen is Messier 37, the salt and pepper cluster. And the one at the near the top of the screen is Messier 38, the starfish cluster. And I unexpectedly managed to also get the Flaming Star Nebula, the Spider Nebula, and the Fly Nebula in the image. And I was intrigued by that green smudge I noticed near the Flaming Nebula, which turned out to be Comet Atlas, which is C2020M3. And this was shot with my Fuji X-T2 and a Rokinon 100mm lens at f4.5. And this was a total of 34 minutes of 1 minute exposures at ISO 6400. And that's our last image for the night. Just a reminder that the Astro Imaging Community Cafe is coming up on December 16, 2020 as well. So that's this coming Wednesday at 7:30 p.m. We'll have a couple of different presentations lined up. So I'll be doing a presentation on planetary imaging using various kinds of equipment. It might be of interest to some people since the December 21 conjunction of Jupiter and Saturn is coming up. And Alistair and Ling will be doing a live demo of Sequitur and how to take a series of fixed tripod shots and stack them. And Stephen will be doing a presentation on using Raspberry Pis for running image sequences. So hoping to see a lot of people there. And this event is actually open to the public, even though normally the Astrology Community Cafes are members-only events. Perfect. Well, thank you very much. And I hope to see a lot more images next time as well. Back to you, Jeff.
Okay. Thanks, Abdur. Okay, that's just about it. If I can get, there you go. A couple announcements. First off, Bruce would like to say something.
Well, if you can hear me.
I can hear you.
Okay, good. I was just going to mention in today's total solar eclipse, first of all, my condolences to those members who had intended to go and see it. In South America, I know there were some of you, and this wasn't the year for it, I guess. Just to note that it marks a milestone between two pretty significant eclipses for us. Today is exactly 1,211 days since the total solar eclipse of 2017, August 21st, that many of us saw the Great American Eclipse. And 1,211 days from now is 2024, April the 8th, when another total solar eclipse travels from Mazatlan up through the central United States and then up into eastern Canada. And again, I'm sure people have plans to go and see that eclipse. Now, this is not an accident. It's actually a period. It's a minor period of solar eclipses called a hepton, which is 41 lunar months or lunations. And eclipses repeat at that interval pretty consistently and at the same type of eclipse, because that period is also almost an integer number of anomalistic months or perigee to perigee months. Meaning if you have a big full moon for a total lunar eclipse, 41 lunations later, you're going to have another big moon near the ecliptic, and you're probably going to have another total lunar eclipse. And I suspect we have members who saw, for example, in 1988 in Borneo, 1991 in Mexico, 1994 November, South America, 1998 February, Aruba, and 2001 June in Africa, Madagascar. Those would all be the same period apart, called a hepton. So it is a common period, and it's very useful for total solar eclipse chasers to know this period, because when you get a long eclipse, there's a very good chance that 41 lunations, about 3.3 years later, one hepton, you will get another total solar eclipse somewhere in the world. And just a final note from Jean Mias on heptons. He says, in such a series, the eclipses alternate. They jump from one hemisphere to the other. So there's two groups, one shifting northward, one southward, cross each other in the equatorial region. So that's what we saw in 91, 94, 98. And so this time around, we have North America, South America, North America. So again, you have the flipping of hemispheres from north of the equator to south and back again at that interval. So anyway, I thought since that eclipse happened today and I watched it on the internet, that maybe some of you would like to know that connection to the long-term pattern of these things. Thank you.
Thanks, Bruce. Okay, got a couple things here for closing announcements. First off, we have some spending proposals that will be discussed at the regular meeting in January. And these are just our regular housekeeping items we do every year. And when I typed them out, I put this year instead of 2021. So we will change that formally. But when you read in Stardust, all these proposals for 2020, they're actually for 2021. Okay, our next meeting is January 11th. It'll be our AGM, and we'll install the new council for the next 2-year term. Have some reports, present the President's Awards, and then it will be followed by an abbreviated regular meeting with exciting spending proposals. And it is also a members' night, so if you have anything to present, let Tom or myself know. As Abdur already mentioned, the Astro Imaging Corner Introduction to Astrophotography is on Wednesday. Details can be found on our website. On January the 20th, next year, we're doing a Zoom forum about how to use a telescope, which we've been doing every year for a number of years in person. we're going to try and do it virtually. And as Abdur also mentioned, I'm sure most of you are following the conjunction of Jupiter and Saturn on December 21st. It will be the closest conjunction of these two planets that has been visible from Earth since 1226. So we're hoping for clear skies. I've been doing a little project of my own of photographing them night after night, but this last week lost 3 nights because of clouds. The loaner program is once more on hiatus due to COVID. Those few months when it was open, after the initial spring lockdown, saw very brisk business. So thanks to James for doing such an outstanding job looking after our loaner program. And as we close out 2020, we look forward to a time when we can once again gather in the Ziedler Theater in those very comfortable chairs and not in front of a computer screen. And we can bring back some of the regular features like Book of the Month, which we haven't been doing because we can't get into our library. And of course, the tasty treats at the mid-meeting break. This meeting is being recorded and will be on our YouTube channel in a few days. So if you wish to go over some of its content again, you can look for it there. Before the pandemic, we did discuss videoing the meetings for a live stream and storing them on YouTube. So when we get back to in-person meetings in the Ziedler, we're going to give that a go. Over the holiday season, please stay safe, follow Dr. Henshaw's advice, and make the best of this unusual time that we're in. Finally, since June, I've closed the meeting with a song. And as this is the last regular meeting I'll be hosting, I thought, what would be appropriate? Some winter song, something for the holidays, Auld Lang Syne. No, I came up with something that kind of sums up the last 9 months, and I'm going to play it right to the end. So whether you say Happy Hanukkah, Merry Christmas, Happy Festivus, Happy New Year, season's greetings, or nothing at all, good night, and we'll see you all in 2021. So here we go.
I ain't been nowhere, man. I ain't been nowhere, man. Been sitting in my chair, man. Growing out my hair. Sleeping, I've done my share, man. I ain't been nowhere. I'm in the bedroom, bathroom, living room, dining room, attic, basement, just to find an old room, a hallway, driveway, same place as yesterday. Go look, read a book, jog around the breakfast hook, class link, get a drink straight from the kitchen sink. Can't think, eyes blink, man, do my clothes stink. I ain't been nowhere, man. I ain't been nowhere, man. Been sitting in my chair, man. Growing out my hair, man. Sleeping, I've done my share, man. I ain't been nowhere. I'm playing Yahtzee, Jigsaw, Scrabble, and Monopoly, Jenga, checkers, Cards Against Humanity, Fortnite, Minecraft, Grand Theft Auto 5, Battleground, Pac-Man, Black Ops, Stay Alive, Obstacle Course with your daddy's old golf ball, Mousetrap, Ping Pong, Happy Hour, Zoom call. I ain't been nowhere, man. I ain't been nowhere, man. Sitting in my chair, man. Growing out my hair, man. Sleeping, I've done my share, man. I ain't been nowhere. I'm watching Netflix, Apple, Disney, and Amazon, YouTube, Roku, Hulu's, Jammies on Tiger King, Schitt's Creek, Maisel, South Park, Star Wars, Star Trek, Ozarks, Getting Dark, Porn, a beta, dirty old magazines, Lysol, quarantine, see what I mean now? I ain't been nowhere, man. I ain't been nowhere, man. Been sitting in my chair, man. Growing out my hair, man. Sleeping, I've done my share, man. I know someplace you used to go. I ain't been nowhere.
Okay, so good night.
Merry Christmas.
Merry Christmas.
Thanks, Aaron. Night.
What's that?
Merry Christmas.
Yeah, okay.
Night.